Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist that I'm calling Continuous Random Variables, and today's topic is the chi-square distribution. To define the chi-square distribution, we let x be a chi-square random variable with degrees of freedom n, which is a positive integer. Then the degrees of freedom for x with n degrees of freedom is given by this function here. It's 2 raised to the n over 2, gamma of n over 2, x raised to the n over 2 minus 1, e to the minus x over 2. This is when x is positive. It's 0 otherwise. Theorem, let x be a chi-square random variable with degrees of freedom n. The mean, the variance, and the moment generating function of x are given by these expressions. The mean is n, the variance is 2n, and the moment generating function is 1 divided by 1 minus 2t raised to the n over 2. And for the proof, I'm going to point you back to a video that I have on the gamma distribution. And if you let alpha equal n over 2 and beta 1/2, then these formulas are exactly what they should be. And the reason this works out is the chi-square distribution is a specific example of a gamma distribution. Next theorem, let x1 through xk be independent chi-square random variables with degrees of freedom n1, n2, nk respectively. Then x, which is the sum of these k independent variables, has a chi-square distribution with degree of freedom n, which is the sum of the n1 through nk. Now we're going to use theorem 6 from video ims32, which is on moment generating function. So the moment generating function of x, which is the expected value of e to the tx, but since it's the sum of independent random variables, it's the product of those moment generating functions of the independent random variables. Well, they're each a chi-square distribution, which has this form. So, and then the product, you sum the exponent and you get this. But if we let the sum of the ni be n, then it is a chi-square random variable because this is a chi-squared moment generating function. And the theorem follows. Let x be a standard normal random variable and let y equal x squared. Then y has a chi-square distribution with n equal 1 degrees of freedom. And the technique we're going to use is we're going to drive the CDF, take the derivative, and then that's the density function. We proved this in an earlier video. Now the CDF function of y is f of y, which is probably the random variable y is less than or equal to some specific value called little y. But y is x squared. We take the square root of both sides, you get this, that x is between these two values, minus square root of y and square root of y. But since x is a standard normal random variable, that's the difference of the CDF functions. We showed that when we looked at the standard normal distribution. Next, we take the derivative of this. Take the derivative of f of y to obtain the density of y, little f of y. So the derivative of capital F of y is the density, little f of y. But if we take the derivative of this, remember this is a CDF function, so the derivative becomes the density, right? So it's little phi, that's the notation for density, standard normal density. Capital Phi is the CDF for the standard normal distribution. But you can't forget about the chain rule, so you have to take the derivative of the square root of y, which is this. Then it's minus, there's a plus here, but we get an extra minus when we take the chain rule, it becomes a plus. So the capital Phi becomes a lowercase phi, but then the chain rule, we get a minus 1 over 2 square root of y, and that minus and the minus become a plus. Now let's plug in what we get for phi of square root of y. And this is it. This is the standard normal density, but it should be y squared, or squared here, but the square root of squared is just the value, so we get a y. This comes down here, we plug in minus Square root of y squared, you just get y again, and then this comes down. Well, there's two of those, so it's 2 times one of those, and then one of the 2's cancel here, and we get this. Now, what I did, the square root of y took to the top, and it becomes, y to the 1/2 minus 1, which is, y to the minus 1/2, which is what this is. And if we rewrite what square root of 2 is, which is 2 to the 1/2, and the square root of pi is gamma to the 1/2, then this is the exact form of a chi-square distribution. And so the square of a standard normal is chi-squared. Now let x1 through xk be independent standard normal random variables. Then let x be the sum of these squared random variables. And it has a chi-square distribution with n equal k degrees of freedom. And I'm actually going to point you back to the previous 2 theorems we proved, which proves this theorem. Now let's do some illustrations of what a couple of these theorems. Let's let n equal 500,000, so 500,000. We're going to take a random sample from a standard normal distribution. So x is a vector of length 500,000. We're going to square each component, store it in y. Let's create a histogram of y. Then over the top of it, let's put a line that's a density of a chi-square random variable with 1 degree of freedom. And we get this plot here. And notice how close they are, as they should be. If we were to increase the number of bins in the histogram, then it would even look closer, than what it really is. It's amazing. Now, as always, I will copy and paste the R code into the comments section. Now, let's do another one. So let's set k equal 10. And we're going to generate a random sample of size 10 from a normal distribution, square each of those, and then sum it and store that in a component of y. We're going to do this 500,000 times. So each component of y is the sum of 10 squared standard normal random variables. Let's create a histogram of that and plot over the top of it the density of a chi-square random variable with 10 degrees of freedom, and look at it. And notice that they agree so much. The bars are the simulation, and the red line is a calculation, and they agree tremendously, as they should. Okay, well, that's all I have for this video. We're at 8 minutes. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.